We can see all sorts of transformations on our trig functions, like vertical stretches, compressions, shifting. We saw one with a phase shift. The one we need to be careful of, though, is when we need to adjust the period for our graph. So that comes through with a number multiplying on the inside of our trig function, because what that's going to do is adjust our formula. And with it, it'll create more or less possible solutions. So the cases we've looked at so far were fairly direct in terms of grabbing the values that we would see pop up on the unit circle. With these ones, we need to dig a little deeper because there might be more solutions than just the ones that we are kind of directly solving for. So we'll go through that with each of these, looking at how do we solve, get kind of our starting angles, but then making that list for all of the possible solutions between 0 and 2 pi and making our formula. Which with these, actually what I'm going to do is form the formula first and then make the list of solutions. That tends to be a bit easier with these. So for solving, we're going to go through the same routine. So like here, I would take the inverse cosine of both sides. Actually, sorry, before I even do that, I'm going to think about the period for this graph. So cosine's typically 2 pi, but when we adjust the period, we take 2 pi over b, which that's the number that's coming up in there, that value for b. So what I'm seeing here is that the period for my solutions is actually over pi instead of 2 pi. So I have that little note to myself off to the side there. Now I'm going to go and solve as I normally would. So I have my angle 2 theta is equal to inverse cosine of 1/2. And then what I'm going to do is go and grab solutions for this inverse cosine of positive 1/2. So if I go to my unit circle, thinking x is positive 1/2, which lands up here and down here, and that's one of our special values. So what I'm seeing here is a positive pi over 3 and a negative pi over 3. So with that, I can go into kind of these two solving scenarios, those two angle measurements. So I could have 2 theta is equal to pi over 3, or 2 theta is equal to negative pi over 3. And then to solve for theta completely, I'm going to divide both sides by 2. So that'll give me that theta can be positive pi over 6, or theta can be negative pi over 6. All right, so before I start listing the solutions on 0 to 2 pi, which I still want to do, I'm going to go and make the formula for this. So I could have the positive or negative pi over 6. So let's go ahead and write that. So for theta, theta is equal to plus or minus pi over 6, and then plus, and then where I was usually going 2 pi, what I'm going to use is the fact that we actually have a new period, which is pi, where k is an integer. Okay, so for listing my possible solutions between 0 and 2 pi, what I'm actually going to do is use the formula to look at all of the different possibilities. So what I want to do is kind of side work. I'll just put this in a little bubble over here. Is that I want to look at taking positive pi over 6 plus increments of pi. So if I go plus, I don't need to write the positive there, pi, which is the same thing as 6 pi over 6. What I could do is see some different solutions. So with these, the denominator is always going to stay the same, but I'm thinking of this as 1 plus 6. So where I have pi over 6 as a possible solution, plus 6 would give me 7 pi over 6 as a possible solution. Then if I added 6 pi over 6 again, that would get me 13 pi over 6. However, that goes beyond 2 pi, because 2 pi would be 12 pi over 6. So for this, I'm kind of looking from 0 to 2 pi, which with a denominator of 6 would be 12 pi, just to give me an idea of actually that goes beyond that, so I don't want to use 13 pi over 6. So I have these two solutions of pi over 6 and 7 pi over 6. Now I'm going to do the same thing, but with negative pi over 6, plus intervals of pi, which is a 6 pi over 6. So negative 1 plus 6 is a 5 pi over 6. Add 6 pi over 6 again, that's 11 pi over 6, and that still fits in our interval. If I added 6 again, so 17 pi over 6, that goes too far past the 12 pi over 6, so that's not good. So I have that 11 pi over 6, and I also have that 5 pi over 6. I do not have the negative pi over 6. So what I'm just using is this formula to see the possible solutions that are showing up in this interval 0 to 2 pi, but it can help to use that common denominator so you can really see where they're landing. So using the formula, I got that list there. So to make it a little bit more pretty, on 0 to 2 pi, we have pi over 6, 7 pi over 6, 5 pi over 6, and 11 pi over 6. So what happens here when we change the period? It's like over here, so we were really solving with that inverse cosine of 1/2, and then when we divided by 2, it gave us these kind of final solutions of positive pi over 6 and negative pi over 6. But then because of the period, we also got the values that are an interval of pi away from those. So we also got those two extra solutions in there as well because of that interval of pi being the new period. So that gave us our, what is that, the 7 pi over 6 and the 5 pi over 6. So that's where with the adjusted period, we just need to be a bit more careful. We can get the standard or kind of the starting values like we did before, but what I would recommend doing is making the formula first and then start thinking about what values does that formula actually give you. And that can give you your complete list, because otherwise that pi over 6 and like negative pi over 6 would have given us the 11 pi. We would have only seen 2 solutions when there were actually 2 more because of that period. All right, let's look at a few more examples with these. So with this, let's see. Let's start with the period because I noticed that 3 in there. So with tangent, our period is usually pi, and I'm going to go pi divided by b, which is 3. So we're working with a period of pi over 3 here. And then I wrote that down. I'm going to ignore it until I get to this part of making my formula. All right, so I'm going to subtract 1 from both sides and divide by that square root of 3. Let's see, minus 1, divide by that square root of 3. And now I have my tangent function is equal to negative 1 over root 3. Take the inverse tangent, and that gives us inverse tangent of negative 1 over root 3. All right, so from our key values for tangent, what I'm looking at here is that case. So again, tangent is the ratio between 2 values. So it's like your y coordinate divided by your x coordinate. And this is coming from a ratio of, we would have 1/2 in the numerator and root 3 over 2 in the denominator. So it's coming from our pairings of a pi over 6 interval. It's just one of them is going to have to be negative and one positive. So it's like we have these possibilities. We could have negative 1/2 over root 3 over 2, which is giving us the coordinate, what, x is positive root 3 over 2, y is negative 1/2. Or the negative could have been in the denominator, so 1/2 over negative root 3 over 2. So that would give us the coordinate negative root 3 over 2 with a positive 1/2. So graphing those, x positive root 3 over 2, negative 1/2 would be there. And negative root 3 over 2, positive 1/2. Right there for tangent, we can see our period of pi there. Since we haven't used the 3 yet, that's why we're seeing our kind of standard period. So let's see, that's a 5 pi over 6 and a negative pi over 6. So going back, now what we can do is split this up into the two possible solutions. So we can have 3 theta is equal to that 5 pi over 6, or 3 theta is equal to negative pi over 6. Now I'm going to divide both sides by 3 and divide by 3. So that'll give me theta is 5 pi over 18, since it's like times 1/3. Theta is equal to negative pi over 18. All right, so I have these two numbers coming up. They aren't angle measurements that we're really used to working. So for making my formula, and yeah, we can go with making our formula here. What I would do is take each of these values and add on intervals of pi over 3. So let's go ahead and write that out. I'll come back to that a little bit, but this would be kind of the long way of writing it out, but it would be technically correct. But I'll show you how we could shorten it later. So theta is equal to taking that 5 pi over 18 and adding on increments of pi over 3 for that period that we're working with, or theta can equal negative pi over 18 plus increments of pi over 3, where k is an integer. All right, so that gets our formula going. So we want to have these starting points and then going based on our period. So if I want to make this list on 0 to 2 pi, we're going to need some fraction math. And something that's going to help me is to take this pi over 3 and make an equivalent fraction with that denominator of 18. So I can actually look at adding those numbers together with each other. So that would take multiplying both by 6. So I'm going to look at this with the 6 pi over 18 increment. So let's see. On 0 to 2 pi, which is similar to if I have that denominator of 18, on 0 to, let's see, if I made a denominator of 18, 18 times 2 is 36. So that just helps me with kind of the, how far I can go, the limit to those, so that I don't go beyond 2 pi. So let's say I take that 5 pi over 18 and I'm adding on those increments of 6 pi over 18. So let's see, I would have that 5 pi over 18 plus 6 would be 11 pi over 18 plus 6 plus 6 plus 6. And if I added 6 again, which again, this 6 is just coming from that numerator there. That's all I'm focusing on, adding 6, adding 6. If I went again, I would go to 35, which is okay. But then beyond that, if I add 6 again, then I'm going past that 36. So I'm going to stop there. So that takes care of this 5 pi over 18 plus those increments of pi over 3. Now if I do this with the negative pi, so that's like a negative 1 plus 6, well that's 5 pi over 18, which we already listed, and then plus 6 plus 6. So actually these line up with each other, meaning what I was saying that I would go back to is really I only need one of these because they land on each other. With other equations, that wasn't the case and we had to list them separately, but what I could do here is get rid of one of them. It wouldn't matter which one, just to make it more concise. You could say just that equation, because like subtracting away that pi over 3 would get you to that negative pi over 18. So that's where you could simplify it a bit. So it takes a little fraction work here, but as long as you can make your equivalent fractions, it's just making those intervals and then kind of knowing the limit to where 2 pi is based on that denominator. All right, let's look at one more here. That was a tough one. This is kind of a nice one to end on. Let's see, for period, we're gonna have with cosecant, the period's 2 pi, and then over b, which is 3. So we're working with a 2 pi over 3. I'm going to need to use an identity here because I don't know what the inverse of cosecant does. So I'm going to think of this as 1 over sine of 3w equals 1. And then I need to get sine out of the denominator there, so I'm going to multiply both sides by sine of 3w. And then what this will give me is inverse sine of that positive 1 is equal to that angle measurement of 3w. And now I can go and evaluate my inverse sine. So on the unit circle, this is telling me I have a y coordinate of positive 1, which is happening only in one spot, which is at the angle measurement pi over 2. So with that, what I can do is just make a substitution there of pi over 2 is equal to 3w, divide both sides by 3, and I get an angle measurement of pi over 6. So if I jump over to making the formula, I have this one angle measurement, and it's just because that inverse only produces one solution. So for w is equal to taking that angle measurement and then adding on the period, which is 2 pi over 3, times k, where k is an integer. So to list out the possibilities on 0 to 2 pi, I'm going to be taking that pi over 6, so that's probably going to be our smallest case, and then adding on increments of 2 pi over 3, so I'm just going to make that equivalent fraction with a denominator of 6, so with that I need to multiply by 2. So we're adding on 4 pi over 6. So if I think about adding increments of 4 pi over 6, which is really just adding 4 to the numerator, so I have 1 pi over 6 plus 4 plus 4 plus 4. However, that goes beyond 2 pi because 2 times 6 is 12, so I actually wouldn't include that last one there. So I'd have 3 angle measurements coming through because of that changed period. So with these, start by finding the new period of your graph. Go about solving as we usually would, and I'll give you your kind of angles to start with. And then before making the list with these, I find it helpful, and you may be able to do this part more easily. It's just different brains approach it differently. But I like to start with the formula and then using the formula to find all of those possible solutions 0 to 2 pi. And with that, it's just a little fraction work to get that complete list.